Hello, my name is Janssen. I work at the Max-Planck-Institut for Iron Research in Düsseldorf, Germany, and today I want to talk about automated ab-initio determination of material properties at finite temperatures using pyiron. Pyiron is our integrated development environment for complex simulation protocols. So the goal here is really to go from an atomistic structure, like you see it here on the left, towards a phase diagram, like you see it on the right, using just simulations, without any kind of empirical parameters or any additional information. Before I start with this, let me briefly introduce the institute. So the Max-Planck-Institut for Eisenforschung, that's iron research in Germany, was founded over 100 years ago and is very specialized in a close collaboration with industry. So we have a lot of projects where we look at materials in the complex environments that they actually use in and how we can understand the materials there. And to do this, we combine a lot of experimental techniques and experimental insights with simulation. So we really try to align experiments and simulation on top of each other to get a better understanding of the materials with this condition, in particular in the special conditions of complex environments. So one tool to do this is by calculating phase diagrams. So here you see the phase diagram for iron and carbon. We have the carbon concentration on the x-axis and the temperature on the y-axis, and you see how the phases change depending on the carbon concentration and temperature. So if you now have want to design a new car and you want to maybe make it larger, you can see, okay, how can I vary the carbon concentration to have a phase transition and maybe get different material properties for a given piece of the car. Right, so we really try to calculate these phase diagrams from ab initio without any kind of empirical information in there. And this is one example. So typically to calculate the phase diagrams, you calculate free energies, that's what I illustrated above. And you see then we take the free energy is calculated as a sum of different contributions. So we start with the total energy, we then add electronic contributions, and we then have quality harmonic contributions, so that's we consider the volume expansion, and then also anharmonic contribution. And just to give you one example where we are right now, here I plot the heat capacity of calcium, so you see heat capacity over temperature. I plot a lot of experimental results, right? All the black dots are in different experimental groups, and then I plot the blue and orange line, which are two different DFT functionals. And we really nicely see that they agree quite well, right? So in particular for the FCC part, we have very good agreement. And then for the BCC part, the theoretical results agree with the lower branch, while the upper branch can be falsified with the experimental results. And this is really important because there are databases, so CalFOT is one of them, which try to store heat capacity information to allow people to fit and construct phase diagrams like the one we saw before. And previously, the CalFOT database included the upper branch. So they basically just evaluate the existing experimental data and then have to decide which branch to trust. And now we have a new tool by using ab initio calculations to really say, okay, no, the upper branch doesn't seem to be in agreement with theory, and we suggested them to use the lower branch, and they updated the database after they saw our results. So we're quite proud of this, to really have this perfect alignment, and I guess it's really nice for me as a student to see, okay, I can not only validate experimental databases, but I can even extend the models and contribute to the overall process like this. So how this is done? Naively, one would say, okay, we start with density function theory, we calculate our partition function, and then from the partition function we get the free energy and can calculate the phase diagram. If you think about it in a bit more detail, you would say, okay, what do we need? We need volume dependence, we need concentration dependence, we need the different phases at different temperatures. We already see that there we have quite a lot of free parameters, resulting in a lot of calculations. We need to identify always the minimal configuration. And then from each of these parameter sets, we still need to do 10 to the power of 6 or 7 configurations, where each of these configurations takes a few hours to compute. So we already see, okay, this is not feasible at the moment with our current algorithms and also with the current computing power. So what we do instead, we take a few DFT calculations. So you see here 10 to the power of 2 or 3. We then fit an interatomic potential to these DFT calculations. And then we use the interatomic potential to do the evaluation of all the configurations. So it becomes a lot cheaper, and we still get more or less the same quality. The important part here is that our interatomic potentials are not transferable. Instead, they are fitted for one phase at one concentration at one temperature. Right? So They're very much specialized there just to have the extended sampling available. On the other hand, so we solve this, we reduce the computational load, but we increase the human load, right? So it becomes very complex. You have to learn DFT code, you have to learn interatomic potential fitting code, you have to learn how to do then the calculation of thermodynamic properties. You can already see, okay, this gets quite extensive for a new student to build up all this knowledge before they can really contribute to the field. And so given this motivation, we really started to say, okay, we need to somewhat standardize this, right? So calculating a phase diagram has to be as easy as calculating phonons or as calculating an energy volume curve is right now, right? So there are default tools that you use to calculate those, and we want the same to have available for the phase diagrams. And this is where we aim with pyiron, right? So it should really be the technical implementation layer, handling the job management, so submission to the queuing system, to your computer cluster, handling the data management, how to store the jobs, what information to store, and also the parsing, right? So what are the output files of a particular code? How do I get total energies, free energies, coordinates? How do I change it? What's the most efficient way to communicate with the code? Like some codes support different interfaces and so on. So it's really this idea of like a general computational layer, and the goal is really that this user can focus on the physics, and then all the technical part should be handled by pyiron. And now for this talk, I really want to pick like 3 steps. I want to start with the density function theory part, then focus a little bit on calculating melting points, like one of the rather complex thermodynamic properties and how we calculate them, and also how we can automate the process of calculating those. And then finally, talking about the implementation in the pyiron framework. So let me start with the DFT part and the challenges there, right? When we started, and also the results of calcium that I showed previously, they were all done with classical EAM potentials, right? So as long as you have only a single element, EAM is very sufficient. It's much better than using the harmonic approximations, like you see it here, right? So you have energy errors of like 30 millieV. If you consider the volume expansion, so going to effective harmonic, you're down to something like 20 millieV, but with the EAM we were plus minus 10 millieV in comparison to the DFT data. But the EAM was limited when it comes to like high chemical compound space, right? So when we looked at high entropy alloys, like you see it here on the left, we really had trouble working with an EAM potential. And we learned there also about the moment tensor potentials from Alexander Shapeyev, and we really like them. They are quick and very precise, and with those we can really achieve like 1 millieV in precision. I'm not going to talk about the details here because Tim Miller already did this yesterday in his talk. But when we now reach this level of precision of like 1 millieV, we really have to ask ourselves, okay, what is the precision of our DFT data? Do we really have a signal at 1 millieV, or is it just we are just fitting noise? Because if we are fitting noise, we could already survive with a much cheaper machine learning model, and this would mean we could accelerate our calculations quite a lot. Right, so this really, the focus is now, what is the DFT precision, and how can we tune the DFT precision? And I guess all the DFT users know this, right? So you would typically take the manual of your favorite DFT code, so in my case it's VASP, and VASP suggests a certain energy cutoff for a given material, so here for aluminium is 240 EV, and it suggests a K-point mesh of roughly 1000 K-points for a single atom. So I take an 8 by 8 by 8 mesh for a single atom, so roughly. And then we say, okay, what does change if we now go to higher convergence parameters, right? So I increase the energy cutoff, I go to 400 EV and 16 by 16 by 16, and then I go even further to very extreme settings of 720 EV and 64 by 64 by 64, all for single atom cells. And what we find is quite remarkable, right? So we still, when we do the first increase in convergence parameters, we still see the shift of 0.01 angstrom. You could say you don't care, yes. Maybe it's not important to optimize to these values, but the machine learning potentials claim to be more precise than this. And if we use a potential which is able to resolve this, we basically waste computing resources when we don't provide DFT data. This has this quality level of information. Here I just plot this in a different perspective. So you now see lattice constant over energy cutoff or lattice constant over K-point mesh. And we basically see, okay, the energy cutoff converge between something like 400 and 500, and the k-point mesh something like a 30 by 30 by 30 or 40 by 40 by 40 k-point mesh. And this is really like the important point here. Recommendations are no longer consistent with modern machine learning potentials. Right? So if you use modern machine learning potentials, you can't rely on the recommendations that you find in the manual of your DFT code. From this, our goal is we want to automate this process. Right? So if we want to automate the calculation of phase diagrams, we really need a tool that determines, okay, what's the energy cutoff and k-point mesh to use, and we basically want to go all the way back, right? So we want to say, okay, I want this precision in the equilibrium volume or in bulk modulus. What are the convergence parameters I should use? So that's going to be the focus of this first part. Can we derive an algorithm which can give me the energy cutoff and k-point mesh if I give it the precision? And I started this by looking, okay, what are the different types of errors that we can see? So we take our typical energy volume curve, again, for iron here, and we fit it with our equation of state. Here I'm using the Murnaghan equation. And these equation of states are basically equations constructed around 4 parameters: equilibrium energy, equilibrium volume, equilibrium bulk modulus, and the derivative of the equilibrium bulk modulus by pressure. And then there are different ways how they are combined, but these are basically typical collections of equation of states. And so we can subtract this fit from the original curve, and then we get this kind of result, right? So that we see that energy differences are fluctuating, and we can identify this as the plane wave jumps. So we can only have a discrete number of plane waves. So whenever we add more plane waves, we can see this kind of jump in energy, and it's not a continuous shift. If we then increase the energy cutoff, we see a rather different behavior. So that's what I demonstrate here. So for an energy cutoff of 950, 20 by 20, we no longer see this high frequency noise, but really more like a low frequency noise. And we can then identify these two. So the high frequency noise, we say, it's like a statistical noise, where the low frequency one is more like a model error. Right? So if we remember, our equation of state has like 4 free parameters, so it can be somewhat identified as like a third order equation. And then what we're missing here is really like the 4th order contribution. And we nicely see the shape of this 4th order term here. And this brings up the question, how do these errors in energy now contribute to the uncertainty in the equilibrium volume, equilibrium bulk modulus, and so on. So again, I take my energy volume curve, I now do have the random noise, and you can nicely see, okay, the distribution is more or less Gaussian, so we assume it really as random here. And now given this distribution, I can construct an error, right? So I just take the standard deviation, or twice the standard deviation, to get an error bar at each point. And then with this error bar, I can again sample the distribution and get the next point at exactly the same volume, right? So I have this orange distribution, this is my original distribution. Now I can create another sample just based on the error bar information. Just sampling this. And this is just very cheap, right? So I don't do any new DFT calculation. Just do sampling. Typically I do it in Python, you can do it in any kind of programming language, but it's a very cheap Monte Carlo-like procedure. So we can not only do one of them, we can do 100, 1,000, and we can nicely create these kind of distributions for the quantity of interest, so in this case, with the bulk modulus, right? And you can see how does the spread in energy relate to spread in the distribution of the bulk modulus. So Monte Carlo sampling is one way that's very good to propagate the uncertainty from the energy scale to the quantity of interest. Second question, how does the model error influence the results? And we can already imagine this, right? So if you go to very large volume ranges, it's going to be difficult for the function to reproduce the exact shape. And if you go to very small volume ranges, the noise contribution is going to be more dominant. And that's exactly what we see. Right? So we see it here. So for the last volume range of plus minus 10%, again, this is the recommendation from the manual. We see we're dominated by the model error. And then only if we go to something like plus minus 5%, it's more or less stable there, and afterwards we have the noise. So we identify this. It's like what we call as like an uncertainty phase diagram. So we have a part where model error dominated, and then we have another part where noise error dominated. And ideally, you want both contributions to be more or less equal. So, how does this now compare to the convergence of energy? Right, so here I have again, now I have energy over energy cutoff. I do it for 1 k-point mesh. I can do it for 2 more, right? So we already see the energy is first decreasing to 16 by 16 by 16 mesh, and then increasing again for the 32 mesh. What's already notable here is really that the curves look very similar, right? So they all have the very same shape, they are just shifted. So we can now take the last values, so at an energy cutoff of 720, and we just subtract them from all the other values. And then plot this here in a semi-logarithmic scale, and we can nicely see that the three different k-point sets really perfectly lie on top of each other. Right? And we can then say, okay, this really hints that the convergence with regard to energy cutoff and k-points can really be separated. So it's really additive convergence here. And looking at the shape, we can easily say, okay, we just fit a linear upper bound to this data to have this kind of prediction possibility. I can do the same for the k-points, but that's not shown on the left. On the inside, you see how the different curves look like. You see again the shift. And with the energy cutoff, it's really like a systematic shift. And we see, okay, for the k-points, that the curves are not so smooth, and we can still use the same methodology, basically construct a linear upper bound for the data. Again, really just to highlight here, we can separate the convergence of energy cutoff and k-point mesh. Now we take these two approximations together, and this is what's plotted here. So you really see, okay, we're just combining these two fits, semi-logarithmic fits. We see this kind of nice upper bounds, right? And sure, one could now say, okay, we could try to aim for this one point between the k-point mesh of 30 by 30 by 30 and 40 by 40 by 40 to get in between there, like for the energy cutoff of 440. But if we remember, this is really just where we come across this point before, but we're not really converging, right? So this is what we do here is really always building upper boundaries and really like a conservative approximation. So it's really the key goal here is we don't want to say, okay, this point you're precise, but if you go slightly away from it, you lose all your precision. We really want this kind of upper bound approximation for our calculations. Now we put the three things together, right? So we have the alternative phase diagram, the separation of convergence, and then the volume convergence, and we can really construct this kind of convergence maps. On the x-axis, we have the k-point mesh, so 10 by 10 by 10 to 60 by 60 by 60. On the y-axis, we have the energy cutoff, and we now see, okay, if we increase both parameters, how does the convergence at this point regarding the error in lattice constant change? And okay, we see, okay, with high convergence parameters, we have the highest convergence, really basically the dependence. In addition to what the algorithm provides, I here plot individual calculations. So these are the dots that you see. And we see that all these dots are really darker than our prediction. And this really just highlights again, we really have like a conservative upper bound, right? So we don't try to be as precise, we really try to have an upper bound on top of the existing data. So with this now, we really have a tool which can be used to get the convergence parameters given the precision that you want, right? So you can now pick a precision, whatever you want. I can tell you exactly what is the energy cutoff and k-point mesh I would recommend to achieve this given precision. So, come back to our picture. Now we have DFT data where we know the precision, we can put it into our interatomic potential, do the fitting procedure, and now let's look into how would we do now calculation of the melting points. So that's the next one. Ethan already introduced this yesterday. So we start by taking a structure, we heat it up close to the melting point, then we have our solid there, right? So it should already have some energy in there. We continue heating until it becomes liquid, and then we put the two structures together. And this is like a typical process. If this interface is stable at a given temperature, we know, okay, this seems to be the melting temperature. So how do we do this? How do we verify it's stable? Yifang Zhu from our department did one paper on this, and she just applied different strains, and then running this part at first constant pressure, then at constant energy, and this gives her, for the different strains, we see it here, the temperature, the predicted temperature over pressure, and we can then look at the point at zero pressure, and then again get a suggestion. And once we did the first iteration of this, we have again a new suggestion for the initial melting point, can plug it in and do the next loop. The reason why we need multiple loops is basically that in the second step we only strain in the z direction, while then when going from the force to this first step again, we also strain again the x and y direction. Obviously, at the moment, we already did this 4 steps and all the different properties, this is an algorithm which is too complex to give it directly to a machine, so it required an expert user, postdoc in our department, to do all the calculations. And so the challenge that we want to address now with this software framework like pyiron is, can we automate this kind of complex level of simulation protocols? And it already started in the beginning, right? So how do you construct a solid interface between a solid and a liquid structure? And in particular, the liquid structure is a bit fuzzy on the right. So how do you put this together without having overlapping atoms, especially high energies, long time to relax, and so on? And the answer is simple, right? So it's all these small steps, but it's important to consider each of them and go step by step. What we do is we start with the solid sample, we reach it close to the melting temperature, but it's not yet molten. We then freeze half of the sample and continue heating the other half. Right? A feature like selective dynamics is currently commonly implemented in all modern codes, but it's something that was not so commonly used previously in multi-point calculations, or what we didn't see before. Right, and then the second question, like, how do you detect where there's solids, where there's liquid? As a human, I can look at this and say, okay, yes, that's 50-50. That's the way how I construct it. But when I give it to the machine, okay, it finds, okay, 20% looks roughly like FCC. There's a bit of BCC where it's not sure why it's BCC coordinated, but then most of the atoms can't identify, right? So they're close to liquid or they're vibrating quite a lot. It's not able to clearly identify the crystal structure there. And again, we can solve this by combining like a kernel density, just smearing the distribution a bit and introducing some kind of threshold here that what you see in the upper part. You can then really clearly identify, okay, it's just like really this 50-50 ratio. But we need this kind of tools to be able to automate the process, right? All this underlying knowledge that you have as an expert user, you have to bring it to the code in some way so we can really make it automated. The same is to identify samples which are fully liquid or fully solid, right? So we just introduce limits, we say 75% is the maximum limit of one part, then we remove the calculation and don't consider other calculations. Or we have curves like this, right? So we try to apply a linear fit on this curve. Where should we fit? Yes, as a human, we would know, okay, we start at something at 1% strain and go down to -5. The machine is not so clear. If we look at the structures physically, how we see that, okay, magnesium, we find this kind of holes there, right? So it seems, in particular for HCP structure, that they form holes when we apply too much strain. Maybe special to this potential, but at least we saw these kind of patterns for multiple potentials. And that's also something we can train the machine, right? So we can say, okay, use the Voronoi volume, calculate the maximum Voronoi volume, compare it to the mean, and once it's larger than twice the mean, then most likely we have some hole there, right? So that's another detector just that we need, okay, to identify the unreasonable, unphysical structures. And then the last part is just having flexibility in the different parameters. So I take a strain, I start with ±5%, I only do 10,000 steps, and then I reduce the strain to get closer to 20,000 steps, and then again I reduce it to 3%, 30,000, 2%, and 40,000, until really I do just 1% strain and 50,000 steps, right? To really sample this point where we're closest to the melting point, to get an even higher precision in the algorithm. So what I want to show you is really that going from, okay, I have a postdoc that can do these kind of calculations, to I have an automated tool, it still requires an additional step, right? So you have to identify, okay, what is the knowledge, how can we quantify these parts, introduce tools like Selective Dynamics, this kind of solid liquid detector, the filtering of the structures, and the flexibility. We did this, and we're now able really to calculate melting points like you see it here, right? So we can iterate over different potentials, do multiple calculations to really get this kind of standard deviation, and then be able to even more precisely quantify the melting point for one potential. So just one highlight again, it really requires deep understanding of how the simulation protocol is constructed. Having done this, just to prove that it's now really working completely automated, we took the database of NIST potentials. We picked roughly 200 of those. Some of them included multiple elements. We then did 260 calculations, 26 elements in total, and really have this kind of nice comparison of experimental results to melting points calculated for empirical potentials. And we can see, okay, there are certain elements where it seems like the potential fitting is very difficult to get the melting point right. There are others where some potentials lie nicely on top of the predicted melting points, and other potentials spread more. And really now it's really like a tool everybody can use, right? So it's now part of atomistic tools. If you want to calculate a melting point for your interatomic potentials, it's very simple now. Good. Come back. So we now saw that, okay, DFT calculations to automate this process is complex, right? To have this kind of automated algorithm. We saw also it's required for the melting points. So how do we do it? How is pyiron constructed to make it easy to develop this level of complex simulation protocols? And the first part was really, okay, let's challenge what we typically do and see, okay, how can we improve, right? And so many people use a command line. We looked around, we really enjoyed working with Jupyter notebooks. We can see the structures directly inside the Jupyter notebook. We can have text and documentation, even literature inside the Jupyter notebook, and also plots and code, all in one document, right? So with this, the Jupyter notebook really becomes like the one simulation protocol where there are all the different steps and all the necessary physics you need to understand. The second part is how is pyiron constructed? So we talk about like simulation life cycles. The user defines a model, project, some kind of generic input. Then the software takes over, translates the generic input to the code-specific input files, calls the executable, runs the simulation, gets the output files, collects them, parses them again to generic output, then does some validation. The validation on the generic level means we only have to implement a given validation once, and we can then apply it to all codes. We then have utilities to collect data, so if you did multiple calculations to collect it there, we can do the analysis and maybe some fitting, just like we saw before, of the energy volume curve. We do a visualization, and that's what we return to the user, and then the user says, okay, he validates the model, maybe does some modification, and it does the next iteration. And internally, this is realized by like an object-based model. So each pyiron object is connected to the user interface, to resources and data storage. The user interface works for the nice representation of inside the Jupyter notebook. We use quite a few fancy features, right, to reduce the number of commands, auto-completion, and so on. The user has to remember. The resource interface connects to parameter databases, the computing clusters, the queuing systems, and the specialized codes. And then the data storage is really use the HDF5 format, which is a hierarchical file format to store all the positions, SQL format to store the dependence of the different objects. And with this, we are able to serialize the object inside this file format, basically store it on one node and then reload it on another node and have exactly the same state of the object. And with this, we really come to this goal, right? So you have to plan, okay, what are the steps, what I should do, maybe what you draw on the whiteboard. You have the same steps in your Jupyter notebook, and it's really a one-to-one match. And just to briefly show this, that the integration of the NIST database or the OpenKIM database, as soon as you assign a structure, so here I create a project can be identified as like a folder. I create a calculation object with the LAMS job here. I assign the structure, I use the iron structure, and then I just got view potentials, and I get 126 potentials that I can iterate over, right? So all the databases are like integrated, really accelerating the workflow. And we have a tutorial on this tomorrow at 11 to 12 p.m. And one part before I close here is really, there are users who are interested in the physics, who want to know all this, and there are others who just want to use a tool, right? And both is fine for us. So if you just want to use a tool, in particular, for example, for the melting point calculations, we really try to make it easy that you just specify a JSON input. Those who are familiar with LAMS, you see, okay, it's pair style, pair coefficient commands. Just what you put into LAMS, you say where the file is located, the kind of elements inside this file, and then which element of those you want to analyze. And then you just call one command, and in the background, we download all the required codes. Everything is compiled, and you can just run it. You get one reply, it's basically the melting point, and then you're ready to go. All right, so we really have now this kind of high-level diagram. You can use it as a black box. That was a scheme that was primarily developed for lab scientists in the field of biology, where like bioinformatics, people develop the tools and then lab scientists can directly use them. For those who want to dive into the physics, we have the Jupyter notebooks. We try to keep them as structured as possible so you can follow each step. The technical implementation, job management, data management, parsers is handled in pyiron. And then we use Conda, which is like one package manager to distribute all the software. Just to briefly show this, Conda allows you just with one line install any kind of package. You can do it for pyiron. What we did as part of this community project is also bringing a lot of codes from the material science community to this, right? So we have LAMPS in there, we have atomic regs, which is a potential fitting code, CP2K, quantum expresso, ab-init, siesta, ab-initio, cluster expansion code like ISET and CLEAS. We have OpenKIM in there, GPOR, PyMagen. So there are quite a wide range of packages that can all be installed in the same way. And if you have more packages, develop your own software and so on, feel free to contact us or contact the developers directly to get also your package integrated. We really find that it's easy to share calculations on particular simulation protocols if you can also bundle the environment with it, right? So there's no need for somebody to identify, okay, how do I compile this certain software? How do I get started? It should all be easy. You should be able to access it directly and just get started. Obviously, that won't not just my work. I really like to thank the collaborators, and in particular Joerg Neugebauer, who initialized all this project, Tilmann Hickel, who is leading the group of computational phase studies, the group of pyiron core developers, and the collaborators. So we're now really at the stage where the project is growing beyond our institute, and it is used at different other institutes. UWI just being one example. Another example is Louis here from Belgium. He started using pyiron as part of his teaching, so for the students, to make it easier to work with this kind of complex codes, just having one Python interface to run the notebooks, and focus really more on the physics rather than the implementation. And I'd like to thank for funding for the DFG, Max-Planck Society, and also industry. So in particular, industry is also interested in this kind of transfer of knowledge that we can achieve with this kind of Jupyter notebooks, right? So one side, transfer of knowledge from academia to industry, but also within industry. They have experts in one department and they want to transfer this knowledge to other departments as well. So with this, I'd like to summarize. So I hope I can convince you that we need this kind of complex protocols, both on the DFT side, as well as for the calculation of finite temperature properties. And with a tool like pyiron, in combination with this kind of package management that Anaconda offers, we can really create a workflow which allows for highly reproducible simulation protocols. And with this, I'd like to thank you for your attention.